Okay, welcome everybody to the second webinar in this series. So today we're going to focus on building software on top of EESSI and contributing to EESSI. I'm Kenneth Hoste. I work at Ghent University in the HPC team there. And together with my colleague Lara, we'll present today's webinar. So just some practical stuff. This is the second webinar in our Spring 2026 series. The webinar of last week, the high-level introduction to EESSI, the recording of that is already available through the link you see on the screen. And you can also use the QR code if you want to get more information on this webinar series. You can still register for the other ones that are upcoming in the next couple of Mondays as well. And as Thomas is mentioning in the Zoom chat as well, we prefer that you use the dedicated channel that we've created for this webinar series in the EESSI Slack to join the questions and the discussions. We will also pick up on questions here in Zoom, but it's just better if you use the EESSI Slack because that let's say brings you to the community already, and you can keep the discussion going also well after the webinar. So if you haven't done that yet, please join the EESSI Slack and the channel that we have for this webinar series. And with that, I'll pass the word to Lara to kickstart the webinar.
Hello everybody. So I'm Lara Peeters, and today I will look deeper into installing software on top of EESSI and also contributing software to EESSI. So we'll first have a detailed look at the EESSI software layer, then a closer look at building software on top and the different tools you can use to do that, and then contributing software to EESSI yourself. Can go to the next slide. So here is an overview of what EESSI can do. So EESSI is the shared software stack. On the left, you can see the different packages that are available in EESSI already. So you have GROMACS, you have a PyTorch, you have R bundles, Python packages, and with EESSI it becomes available anywhere where CERN-VMFS is installed, and it's also the EESSI software stack is set up. So that's on your laptop or your PCs, on your national or regional HPC systems, but also now on the Euro HPC systems, especially through the federated software, EFP, the European Federated Platform, where EESSI is the main software stack. Then also in the cloud, you can easily set up a new instance and have software available within minutes on AWS. And then also just your Raspberry Pi. You don't need to compile the software yourself anymore, so you can just run packages like GROMACS, which would be almost impossible to compile on an actual Raspberry Pi. But now can run. So this is a high overview of EESSI. First of all, we have our file system layer through CERN-VMFS, which we use to distribute our software. Then we have a compatibility layer. First of all, this is like ground level libraries, which we use to build our software on top instead of relying on the host operating system, which means that our software layer, our software becomes portable and you can use it on any Linux distribution. And on top of that compatibility layer, we have our software layer with optimized applications and their dependencies. With the compat layer, we can separate ourselves completely from the host OS, but we have some cases where we do have to rely on some things on the host operating system, for instance, for GPUs, but also maybe if you want to inject some MPI libraries, but we'll go maybe a little more deeper into that later in the presentation. And then for testing, we also have our own reframe test suite, because we really want to make sure that the software that we provide to users is really functioning well and can be reliable. EESSI now also already supports Intel, AMD, ARM, and RISC-V to our development repository. Yes. So today we'll be focusing on the software layer for optimized applications and dependencies. So how to install on top of what is already there on this in the software layer, but also contributing your own stuff so that you don't have to install it on every system where you need it. If it's if it can be if the software you need can be distributed, and if it cannot, we will show you a number of ways to install it yourself. Yes. So this is an overview of the available software. We currently support more than 2,000 software installations. No, there are more than 2,000 software installations available per CPU target via our repository. We will support 15 CPU targets, ARM, as I told you before, ARM x86, RISC-V, we have 750 different software packages that we support, and on top of that, we have over 3,000 extensions such as Python packages and R libraries, which is also it is included in those 750 software packages. So that brings a grand total of around 30,000 software installations that we today have. And this includes software like GrowMax, Lamps, Homegrown Foam, and many, many more. We currently have 2 versions of EESSI that we are supporting. The versions of EESSI 23.06 and 25.06 mainly refer to the version of the compat layer. And then in those on top of those compat layer for 2023.06, we are supporting 2 tool chains, FOSS 2023A and FOSS 2023B. And for our EESSI 2025.06, we're supporting FOSS 2024A, 2025A, and 25B. If you are wondering, is the software that I am using already available in EESSI, then you can go have a look at our documentation where we have an easy way to see if your software is already there. You can search for the software you want, check if the software is there for the CPU targets that you have yourself, in which versions they are, which command you need to load the module and stuff like that. Here is an overview of all the available software over the 2 versions. So on top we have our 2023.06, which now has around 16,000 software installations. This is now stagnating in the end of this year, since we're now focusing more and more on the 2025.06 and getting to a similar number of software packages that we're supporting as we have in 2023.06. So in 2023.06, we now have around 1,200 modules that we have, and that's about more than 600 unique software. And then in 2025.06, we are now over 400 unique software packages. So we still have some catching up to do, but we're working on it, and it's a working project for this. So which are supported CPU targets? So for x86, we support 5 generations of Intel CPUs, as well as Skylake, Cascade Lake, Ice Lake, and Sapphire Rapids. And if you have a CPU that is newer than these generations of somewhere in between, then our auto detection will also make sure that it will pick the best compatible and the best the most optimized software that is possible on your system. Then for AMD, we support 4 generations of CPUs, Zen 2, Zen 3, Zen 4, and Zen 5. Then on ARM, we also already support forced microarchitecture. So we have support for Fujitsu A64FX, NVIDIA Grace, and then also Neoverse N1 and V1. We're also both for x86 and ARM. We have a generic fallback software stack, so that when there's no match for your CPU target, that you will always have something. For instance, on a Raspberry Pi, you will fall back to a generic. Then, as I mentioned, we're also supporting RISC-V CPUs. This is a work in progress. This is not available through softwareeasy.io, but through a separate repository called dev.easy.io. This is not available on all the systems where software.easy.io is already available, but yeah. If you want to try RISC-V, this is also possible. Yes. Then we're also supporting GPU targets for NVIDIA and CUDA. We're supporting different generations of GPUs based on the CUDA compute capability. We're supporting for 2023.06, we're supporting CC 7.01, 8.0, 8.0, and 9.0. And for 2025-06, we're also supporting Blackwell 10.0 and 12.0 on top of it. For using our GPU software stack, we're not allowed to distribute the GPU drivers because of the CUDA license. So you have to do some things on your system to make sure that the GPU drivers are made exposed to easy so that you can use our GPU software stack. To get a full overview of what you have to do to make the GPU stack available, you can check out our documentation on this. Then for AMD ROCm, this is currently a work in progress. It's now also included in Easy Builds. We have a PR for ROCm 6.4.1 merged, and this will be included in the next release. And so we're very actively working on getting also ROCm support into Easy. If you want to get like a closer look at our GPU support, then you can check out the slides from a talk by Casper 2 weeks ago at the AUM, at the Easy Build user meeting in Portugal. The slides and recording are available via the link. So what is special about the Easy software layer? Software installations only link to libraries from our compatibility layer or other installations in the software layer. It does not include any host Linux operating system. Because of this, these software installations become usable on any Linux distribution and become portable to them. We do this via RPath linking. We also have made build tools aware of alternative system roots like sysroot. Some exceptions, like for GPUs, have to be made, and we've also built in different stuff in our software layer so that this is possible, that you can include your own libraries where necessary instead of relying on the libraries shipped in Easy. And with this, we get containers without the containing. So we have a movable, portable software stack without actually relying on container runtimes, which can make sometimes running in an HPC environment difficult. Since we have so many software installations and we have so many targets, it's almost impossible to do this manually. So we have built out an automated procedure via our Easy Build deploy bots. So all the software installations in Easy are built with our bots. Nothing is added, nothing is done manually on that part. The whole installation procedure is semi-automatic, so everything is done by the bots, but there is a human in the loop to do checkups throughout the process. You can you can talk to the bot via our easy software layer repository. This is also where you open PRs to have new software. One of the people builders in the easy community can trigger the bot. So as a normal contributor, you won't be able to talk to the bot and make him do stuff, but somebody from our team has to do it. All contributor, if you want to contribute to easy and you don't have access to all the CPU targets, this is not necessary. We will help you if there are trouble on certain CPU targets where you don't have access to get that software also deployed in easy. But we'll talk more on this later in the webinar. Yes. Yeah, and I will leave it to take a closer look at GrowMax and all the stuff that we do to make easy portable.
Yes. Okay. Thank you, Lara. So indeed, let's take a closer look at a hands-on look to really understand what's going on here. I'll first cover the slides, and then we'll do some poking around in the terminal to really point things out. So what we're going to do is look at the GMX binary of the GrowMax installation in Easy. It's just an easy target. GrowMax is a pretty familiar software package in HPC. And the GMX binary is an easy target, let's say, to take a closer look at it. So the same story goes for any binary really we have installed in Easy. So what we want to do is take a closer look at the binary specifically and see how it's able to find all the libraries that it needs in order to run. So for this, we're going to use standard tools like readelf and LDD to inspect the binary, let's say, and see how it's constructed so it actually works on any Linux distribution. So we'll look at the RPAT section of the binary to show how it's able to find all the libraries, and which also means essentially that an environment variable like LD library path, which is often used to specify to a binary where it can find its libraries, is totally irrelevant because the paths that are required for finding those libraries are essentially hard-coded into the binary itself. And as you will see when I do the hands-on demo, all libraries that are required by GMX are coming from Easy, either from the compatibility layer or from the software layer for specific dependencies that GrowMax has. And all of this is standard Linux, so we're not really inventing anything new here. We're just using the tools and the capabilities that Linux already has to make this work. So what I will do to start off with is just to initialize my session to use Easy. So I'll just do the standard source command to set up the environment so Easy is available. And I can then load a GrowMax module and check that we have the GMX command indeed available. So let me start off by doing that. So in here, this is actually an ARM Linux virtual machine in Amazon. But the same type of procedure will work fine on any Linux system where Easy is available. So let's first check it is there. That's working fine. Let's do the source command let's use the older version here of Easy. Although we do have GrowMax in the newer version as well, so this will also work. So this detects that we have a Neoverse v1 compatible ARM CPU. And with that, we have a actually a couple of GrowMax modules available. Let's pick one of them, doesn't really matter which one we use. Load that GrowMax module. And then with the which command, we can see that we now have indeed a GMX binary available in this long path that is coming from a specific version of Easy from the Software Easy repository, softwareeasy.io repository, the 2023-06 version of that, and then a GrowMax binary that is specific to the CPU that we have that was detected. So now let's take a closer look at this. Let's use readelf -d. And this is going to generate a lot of output, so let's pipe this through less. So what we're now doing is looking at some of the ELF binary format details of that specific binary and see what is in here. So to start off with, it lists a couple of libraries that are required by this binary. For example, libgromax, so the Gromax library itself coming from the Gromax installation, but also needs an MPI library, it needs the C++ standard library, the math library, the C library, and so on. So all of these somewhere need to be found on the system. And the next line actually shows you the long list of paths that are baked into the binary itself to help the loader, the binary loader of Linux, find these libraries. Now, this is a bit of a wall of text, so let me do some grabbing and some cutting like this. Yeah, to make this a bit easier to digest. So this is just cutting things into separate lines, one path per line for that RPath section. And this shows that there's actually different types of paths that are baked into the binary itself here. The first ones are override paths. So you see this RPath overrides in this special location called host injections. We won't explain this in detail, but this is essentially a mechanism that we bake into the binaries. So you can inject your own, in this case, your own MPI library yourself. So you can build a customized OpenMPI library and basically give that to EESSI and make sure that your library is used rather than the one we ship with EESSI itself. So this is a mechanism that allows that. And this is done in a controlled way because the actual location where this points to, so this is actually a symbolic link, which is called a variable symlink. And the system administrator determines where this path actually points to. So you as a regular user, you cannot, of course, come with your own MPI library and inject it happily into the system. But the system administrator can set things up so that's actually possible. So this is one mechanism that's already baked into the binary. The next paths are then more standard, let's say. So these are just the standard locations of libraries in the Gromax installation itself, both in lib and lib64. This is essentially the same thing, but then relative to the location of the binary. So $origin is essentially like a placeholder to the path of the path of the GMX binary, and then relative to that, you can look for lib and lib64, which will essentially bring you back to the same paths as are here, but that's not always the case. Then below that, you see the locations of all the dependencies that we have in the software layer. So this part here tells you that these are all paths in the software layer of EESSI for all the dependencies that are either part of the toolchain or are a direct dependency of Gromax itself. A notable one here is OpenMPI, for example. So this is where it will find its libmpi.so library. So this is a long list of paths here. And if we drop a bit lower, we'll also see the compatibility layer popping up. So this is where it gets things like glibc or the math library libm and so on. So this is essentially a long list of paths that are baked into not only this binary, but every binary that we build with EESSI. And that way we make sure that it's picking up the right libraries, the ones that we actually want to use. And this becomes very visible when you do an LDD on that same binary. So if you run LDD, it will tell you for each of the libraries that are being picked up where they are coming from. So you can see libgromax, for example, is indeed coming from the software layer of EESSI from that Gromax installation. So that's not a surprise. Same thing goes for OpenMPI. So in this case, there's no custom libMPI that's being injected. It's just the standard one that is a part of EESSI itself. And another nice example here is the C library libc. And you can see that this one is coming from the compatibility layer of EESSI. So it's not coming from the host operating system, but it's actually coming from EESSI itself because we take full control over that via the RPath section of the binary. So this tells you that everything is essentially hardwired and we have things fully under control. So that's also what the slides here say. So with readelf, we can check the needed section to understand which libraries are required. We can check the RPath section to see the long list of paths that are being considered by the loader. And we saw different groups of paths in that output. So these host injection paths to allow you to inject specific libraries. libraries in the software installation directory itself, both absolute paths and relative paths. There is $origin placeholder, and then dependencies in the software layer itself, and then as a fallback, let's say the easy compatibility layer as well, which is used for things like libc and libm. And then with LDD, we could see that all these libraries were indeed coming from EESSI. So that's essentially revealing some of the magic that we have in EESSI in that software layer and making sure that everything is hardwired to the compatibility layer. Okay, and I think with that we can switch back to Lara.
Yes. So how do you build software on top of EESSI? You have to make sure that your things have to be set up correctly so that you're actually building as we do in the compat layer so that it keeps portable, otherwise it might be too brittle. And that you also have the RPath linking that we do. This might be a technical challenge and it's probably different from how people are usually building their software. Usually they're just setting specific library paths via the -L object, L option, or via library paths, so that it then at runtime relies on standard systems, RPath or LD library paths. But yeah, okay, I think the next slide. So for building software on top of EESSI, we have plenty of options. The first option is EasyBuild, as we do for our central software stack. EasyBuild should be configured correctly so that it does all the things that is necessary for that it will build on top of our compat layer. But I will talk about this later. You can also manually build on top of EESSI. For this, you need to also configure and set up RPath linking so that you will rely on the compatibility layer. But we also have some tools to make this easier, which we will also come back to. You can also use spec. Kenneth will later show you, hopefully, one of the cases that it's work. And in this case, you can make a database of the provided software packages in EESSI and register as them as external packages so that spec will rely on what is in EESSI instead of building it themselves. Yes. So building software on top of EESSI with EasyBuild, we have made a couple of over the years we have made a bunch of enhancements to EasyBuild to make it easier to manage building software for EESSI. We have improved support for RPath linking, and since EasyBuild 5.0, this is now also the standard way that this is a default setting, so everything that is now built with EESSI should have RPath linking in place. Then we've also added some configuration options in EasyBlock so that they're aware of sysroot, so that it can rely on the different root operating system instead, like we have in our compat layer. Then we also have added support for EasyStack files, which we'll have a closer look at later, but which we use to manage all the installations that we've already done to have a record of that as well. Then we've also added the sanity check only option. This makes it easy to test if software is still working by running the sanity check of the installations that we also already run when it's installed. Then we've also added a from commit option, which is more reproducible than the from PR, since a PR can change over time, but the commit will stay the same. And we've also added a CUDA sanity check to really make sure that all the GPU software that we ship is working correctly. For a recent introduction to EasyBuild, you can check out the webinar that we did last year, Introduction to EasyBuild in the spring of 2025. So for building software on top of EasyBuild, we have a tool which makes it easier to configure EasyBuild. It's called Easy Extend. The module is also shipped through Easy. So once you've set up the Easy environment, you can load the Easy Extend module, which will pre-configure EasyBuild and also load EasyBuild. It's very useful when you're doing local installations on top of Easy with EasyBot or testing stuff. Yeah, so that you're sure about all the configuration is set up correctly. A basic usage of it, I have now already explained a little bit, but you first initialize Easy. You can also set up environment variables, Easy install environment variables, which you can set if you're installing for a user or a project or site. We'll go more into that in the next slide. Then you load the Easy Extend model. You can check out the EasyBuild configuration and see all the configurations that we set in the background. And then once you have set it up, you can start building with EasyBuild with the easy configs. The EasyBuild deployables also use Easy Extend, so this mechanism is very well tested. For detailed documentation, you can check out building on Easy. So as I mentioned in the previous slides, we have some variables which you can set Easy and then something else install. So with Easy user install, you can set in your account and then it will set up the environment so that only one user can use it, so the person that is installing it. So the big difference between the different environment variables is the permissions that will be set on the installations. There are also Easy Project install, which will make it more available to different users via group writable installation directories. And then we also for site-wide installations. So if you want to make software available for all your users at your site, you can also use this one. If you have your own BMFS repository, which you will use to build software on top of Easy, then you can also set Easy BMFS install. To get a closer look on all this stuff, you can check out our documentation using the Easy Extend module. Yes. Maybe before I give it back to Kenneth now, we can check if there are some questions in Slack or in chat.
Yeah, there was one question in Slack, I think, which has been answered already. A question on the differences between the different versions of FOSS. So I guess there's people not very familiar with EasyBuild yet. So the FOSS is a compiler toolchain, and different versions of FOSS essentially mean different versions of the compiler, of OpenMPI, of the BLAS LAPACK libraries, and so on. So there's definitely some room for confusion between toolchain versions and easy versions, but yeah, we try hard to avoid those confusions. And one last thing here we're mentioning on this slide is that you essentially pick one of these four options. And if you don't pick something, Easy Extend will do a sensible thing by default. So it's good to always check your active EasyBuild configuration after loading Easy Extend, as I'll show in the hands-on. So you're actually sure that you're happy with with how EasyBuild was configured. So as a first hands-on demo with Easy Extend, I want to show the installation of an existing Easy config file, which is included in the latest release of EasyBuild, but which is not installed yet in Easy. So nobody has, at least until today, has opened a pull request to add this version of scikit-bio, so 071.post1 is available in Easy, but is available in EasyBuild, but is not installed in Easy yet. So what I want to do is show how you can at least test this installation locally, and maybe prepare to make a pull request, a contribution to EESSI, which we'll do towards the end of the webinar. So all we're doing here is essentially, again, setting up our environment. In this case, we're going to use EESSI 2506 because that's where this toolchain is already available, and some of the dependencies that Scikit-Bio needs are also already available. We'll set the EESSI user install environment variable to a subdirectory of our home directory, because this will be picked up by EESSI extend to pre-configure EESSI build in a sensible way. And then we will load EESSI extend, inspect the EESSI build configuration, and then try the installation and see what happens. All right, so let's give this a try. I'll reset things here in this session. Let me make a subshell as well to make it a bit easier later. So step one is the source step, again, to set up the EESSI environment. I'll use 25.06. In this case, and if all goes well, we should see that the 2025A version of FOSS is already available. So that's very useful. The next step is then to set the EESSI user install environment variable. And in this case, it points to an existing directory where I've cheated a bit because some things are already installed in here. So this already has a whole subdirectory structure here, and some modules you can already find in here. So these are essentially the dependencies of Scikit-Bio, which are not installed in EESSI yet, but which I have pre-installed here to make sure the demo is a bit faster. So there are some dependencies missing for Scikit-Bio, and they are pre-installed, but specifically in my account in my home directory here. All right. Then the next step is to load EESSI extend. So right now, there's no modules loaded yet except for EESSI itself. There is one single EESSI extend module available for each version of EESSI. At least today, there's an EESSI extend that pre-configures EESSI builds. There may be additional EESSI extend modules that get introduced later, but for now, this is all we have. So I can just load EESSI extend without specifying a version. And if we now check module list, we'll see that EESSI extend is loaded, of course, but also EESSI build is loaded. So the latest version of EESSI build, that is, of course, a part of EESSI itself, is now also available. So we can check the version. That should be no surprise. 5.3 is the latest EESSI build release. But we can also check the configuration. And this will tell us that with EESSI extend, we have pre-configured EESSI build to install on top of EESSI. You can see this in a number of ways. For example, here the sysroot, so this is what Lara mentioned, already points to the compatibility layer of EESSI. So EESSI build knows that it's being installed on top of the EESSI compatibility layer. The installation prefix here, we specified an user install. So in this case, it points to exactly this directory that we specified in EESSI user install. And it actually adds a bunch of things after that, specific to the EESSI version and specific to the CPU architecture that we are building on. So if you have a shared home directory, for example, across multiple different types of partitions with different CPUs, you can use EESSI extend and things will be disentangled the way it makes sense. Another thing here, permission related, is a UMask. So the installations are only readable and writable for the user and not for anyone else. And we'll also mark the installation directories as read only after the installation. So there's a whole bunch of stuff going on here. Other things are hooks, for example, the EESSI build hooks that we have in EESSI to customize EESSI build a little bit. Filter dependencies is another thing. So we tell EESSI build not to install certain dependencies because they are already a part of the compatibility layer here. So you can see that this will be quite complex to manually configure EESSI build. And that's exactly why we have EESSI extend doing that for you. And then let's take a look at Scikit-Bio. So we're looking for the Scikit-Bio with FOSS 2025A. And this EESSI config file is actually already part of the EESSI build installation we are using. If I do a -- missing on this, we should see that actually only Scikit-Bio itself is missing. Because I've cheated a bit and some of the dependencies are already pre-installed. In this case, if I would give it the different install paths, like temp user, which is probably empty here, you'll see what is actually missing in easy. And for some reason, it keeps showing me stuff. So I guess this is not as empty as I thought it was. Okay, whatever. So it is able to find some of the dependencies already. Maybe this is really the only thing that's missing. But what we want to do is do a test installation, essentially in our home directory. So it's going to reuse everything that it finds from easy, and it's going to do a local test installation of scikit-bio. And at least this will tell us that it works on the ARM Neoverse v1 architecture here, if this finishes. This is going to take 2 or 3 minutes, because especially the testing step of this takes a little while. But you'll see it's running through the different extensions that are required for scikit-bio. It will get to scikit-bio itself in a bit here. There it goes. And then at the end, it will actually be running a couple of tests, and that takes a minute or two. But in the end, this will finish just fine, and it will tell us that it's working. So this is a first step towards making sure that we can add a new installation to Easy, testing it manually first with the help of Easy Extend. Let me quickly go back to the slides. There is a second demo as well. So this was relatively easy because the easy config file that we needed is already included in EasyBuild itself. So let's say the biggest effort towards adding support for a new software package or a new version of a software package was already done. If you want to do this for the very latest version of scikit-bio with the very latest toolchain that we have in EASY 2506, there's a bit more work because then there is no easy config file yet. And then we need to create one. So I'll let this finish first. I don't want to interrupt it. Let me switch to a different shell. So same type of setup here. Same Neoverse v1 CPU. I will do the same user install like this, and then load easy extend. And if we here search for scikit-bio with a 2025B toolchain, the result will come back empty. So in this case, we don't actually have any easy config files available. So that means if we do want to add this version with this new toolchain, or the latest version of scikit-bio with this new toolchain, we need to create an easy config file for it. Now, I did that just about an hour before the start of the webinar. I've opened a new pull request to easy build for the latest version of scikit-bio and the missing dependencies that were there in easy build. This Cython one turns out to be critical because the existing Cython doesn't work actually for scikit-bio, so I had to introduce a new version. So this adds 4 easy config files. And with this pull request, I actually have enough to already start testing the installation on top of easy as well. So because I have a pull request open, I can just do from PR, check what is missing. So dash capital M or dash missing is the same thing. And in this case, again, only scikit-bio itself will be missing because I pre-installed a bunch of things. And we can try this installation and see if it works. In the end, it should. And if that result comes back positive, we can then conclude we have done enough testing to try and make the contribution to easy and see if it works for all the CPU targets that easy supports. So we'll get back to this later, actually, when we look into contributing something to easy. I'll actually make the pull request to easy and show the steps that are being taken there. In the meantime, our previous one here, the existing easy config file, has worked just fine. So this gives us enough confidence that we can open the pull request to get it into easy itself. But we'll get back to that. All right, so with easy extend, we've done 2 demos, installing an existing easy config file, installing a newer version of software after creating an easy config file first, and opening a pull request to easy build for that. And very similarly, we can test both with the help of easy extend. As Lara mentioned, there's other ways of doing installations on top of easy as well. One particular one is doing manual installations where you can literally unpack tarballs, run compiler commands, run make, and so on yourself. But here you have to be a little bit careful. You have to make very sure that the installation that you're doing is sitting on top of the EESSI compatibility layer. And that everything is being properly linked to make sure that the installation will actually work the way you expect it to. So for this, we have to make sure RPath linking is used and that we're not relying on LD library path at runtime, and that we're really using all the libraries that are available from the EESSI compatibility layer. For this, so for manual installations, we also provide a module called build-env, which essentially sets up your environment to make that process a bit easier. So it does two things. It sets a bunch of environment variables, very similar to what EasyBuild does. So things like $CC, $C flags, and so on. And then what it does underneath the covers, it also injects RPath wrappers. So it essentially replaces the compiler command, or actually wraps around the compiler command to make sure all the RPath linking is done, and that you don't have to worry about this. So also here I have a short demo prepared. So what we will do here, we want to build this libpng demo using make, and we want to make sure we do that properly. So using all the libraries and either coming from the EESSI compatibility layer or from the EESSI software layer for dependencies. So we're loading a module, a libpng module coming from the EESSI software layer here, and we want to make sure this is the libpng we're actually linking to. So let's take a look at that hands-on as well. I'll do that in here. I will clean up my environment, unload easy extends, and unload easy build because we won't be using these. We'll keep easy around and we'll take a look at the build-env module. So you can see there's different versions of the build-env module for the different toolchains that we have. We'll go with the very latest one. So I will load this module. Before I do that, let me show you the impact of this as well. So if we check before loading the build-env module, which GCC versions we have available, we'll see that we have, I should do -- version. We'll see that we have GCC 13.4 coming from Gentoo, so from the EESSI compatibility layer. And we have another GCC that is hidden that comes from the host operating system, which in this case is, I'm going to guess Rocky Linux 8. When we do load the build-env module, and I check this again, you'll see that things have changed. So I now actually have an extra GCC available, a more recent one, which is installed in the EESSI software layer. But on top of that, I also have a wrapper script, an RPath wrapper script. And this is actually the GCC commands that we're using. If we just do which GCC, you'll see we're actually using a wrapper script that wraps around this GCC binary. So after loading the build-env module, if we then run module list, you'll see that things have happened. A bunch of things have been loaded. The FOSS toolchain has been loaded. All of its dependencies have been loaded, including the GCC that we will be using. And of course, the build-env module itself, which sets a couple of environment variables like CC, C flags, and so on. And next to these, it also fiddles with path to inject these RPath wrapper scripts, which are in different locations. Now, the good thing is GCC works as expected. Even though this is a wrapper script, you can just use it as you're used to. Use the -- version, or just use it to compile C programs or C++ programs. It will work just fine. So whatever is calling GCC doesn't actually know it's calling a wrapper script. Now let's see this in action. We've loaded build-env. We'll also load libpng as the dependency we want to use to try and build this libpng demo. Make sure I'm in an empty directory to do that. Yes. So we'll clone that libpng demo, and this is a very minimal example. It's a single C++ file with a make file. The make file just calls GCC, so it doesn't actually know it's being built on top of EESSI or anything. But that's just fine. We don't need to change anything. We can just run make. And here is actually the make file detects what type of libpng it is using. So it calls what was it again? libpng config. So it figures out some things from the libpng installation itself, but it doesn't try to do any RPOT linking or anything special. It just does regular linking with the libpng library here. So with this regular minus capital L and the path to the library, and then the minus small l for the PNG library itself. But if we're not careful and if we don't set LD library path to include this path, things will break. Now, thanks to our RPOT wrappers, that's actually not the case. If we do a read elf on the binary that was built, this target PNG demo, read elf minus D, push that through less, we'll see that an RPOT section was actually injected in here. So this is our RPOT wrappers doing their job. They're making sure that the same host injection paths, but also the location to the libpng library, which is in here somewhere. It's a bit hard to find here in the middle. So the path to the libpng library, libpng dependency that provides the libpng library is actually in there as well. And also when we do an LDD, we'll see that that's indeed the case and things have been RPOTted the way we expected. So both libc and the libpng library are under control of EESSI and are not just coming from a random place on the operating system. So that shows that the build env module is also very useful even when doing manual installations and not using EESSI build. So this is, of course, a bit less tested. I mean, it works as far as we know. It's also documented in the EESSI documentation, but we're not using this mechanism ourselves when building software for EESSI. We use EESSI Extend, as Lara already mentioned, and that's why we recommend generally to use this EESSI Extend approach. There is one more option, and this is something we explored quite recently, is to use SPAC on top of EESSI. So the idea here is to use a totally different installation tool like SPAC, but make it aware of all the installations that are already available in EESSI, so it doesn't need to rebuild everything that it needs. So we want SPAC to use existing installations from EESSI as dependencies. So there was actually quite a bit of work done to make this possible because SPAC needs to know all the details about what is installed in EESSI before they can actually use them. And Loris here has made a detailed proof of concept of this, which is very well documented in this blog post. And he also set up a repository called Spood, which I should actually show, which actually steps through the whole setup that you have to do to make this work. So Spood is a tool to spider EESSI and then weave its dependency web into SPAC. So Spood is a type of spider. This gives you all the details here. I won't step through the details in the repository, but I have a quick demo of this also prepared. So what I will do here is 2 steps. First of all, I will install SPAC because we'll be using this to install software. The important detail here is that we actually need a patched version of SPAC. So Lotus had to make some small changes in SPAC to make things work correctly on top of EESSI. And there's an open pull request, at least one, that is waiting to be merged. So hopefully this necessary change will be included in an upcoming version of SPAC. But for now, you need to use a small patched version. So I'm using Loris's fork of the SPAC repository here. And I'm checking out the EESSI branch in there before then setting up SPAC for usage. So let's start with that part. Okay, let's also do that in here in a temporary directory. So we start by making sure to start afresh because we actually need the older version of EESSI for this. At least that's what the proof of concept was built on top of. So we'll start by cloning the SPAC repository. This will take a little while because it's downloading quite a bit of things. We'll set things up here using that EESSI branch. And once that is done, we'll then clone the Spood repository itself, set up the EESSI environment, and then just run the quick start script. And I'll show you what is actually in there. So as soon as this guy is done here, I can complete the setup. So all the details on this are in this blog post here as well. It's actually a pretty detailed discussion of what's going on, what you need to do. Underneath the covers, we're essentially exposing the installations that EESSI has to SPAC with a setup like this, where we have a packages.yaml file that tells SPAC about all the details. For example, for GCC, which version is it, where does it live, which compilers does it provide, and then also for common dependencies like OpenBLAS, the similar type of things. Also for which CPU architecture is this installation built, and so on. So we need to build up a file like this, which can actually eventually be auto-generated. For now, it was created manually for the proof of concept, but the idea is to auto-generate this in the end. So here we need to check out the EESSI branch, and then we need to set up our environment for using SPAC. So at least SPAC version works. All right. And then we need to clone the spud repository. This is quite small. And let me make sure I'm not overlooking something. Yeah, here we need to source the EESSI environment, 2306. And then we're ready to run this quick start script. So this will do a whole bunch of things, and it will actually tell us step by step what is going on. So let's just run it. So this creates a demo spud subdirectory. It copies a bunch of files, including this packages.yaml file, which you can inspect. So this is what is actually exposing software, or all the software that will be used for this demo, to SPAC, as it is available in EESSI. It's then doing some bootstrapping of SPAC itself, which shouldn't take too long. And it will proceed with then doing a SPAC install of Quantum Espresso, and wrapping up with showing that everything is actually coming from EESSI. This will take a bit of time, so I won't wait for it, but the end result is in the slide here. So eventually, this will do a SPAC install Quantum Espresso of the very latest version. And this will take a couple of minutes, and in the end, it will do an LDD on the Quantum Espresso binary to show that really everything is coming here from EESSI, except for Quantum Espresso itself, which is in the installation directory that SPAC has created. So this essentially shows that the idea at least works, and there's a bit more work necessary to make this very reliable and very robust. All right, so that's the 3 ways to install software on top of EESSI. I think we can switch back to Lara now for the end of the presentation.
Yeah, so let's now have a closer look at contributing software to EESSI. The following must be taken into account. So to contribute to EESSI at this point, you need an EESSI config, because we built everything at this point with EESSI build. You should either have an EESSI config should either be in the latest release of EESSI build, or there should be a merge pull request to EESSI build with your EESSI config. A pull request must be open to EESSI software layer for it to be installed. And we have together to have a full view of our EESSI contribution policy that must be followed. You can check out our documentation. The software must be redistributable, like open source. It must work on all CPU targets. It must be built by the EESSI bot, and it should be a recent version of the software with a recent toolchain. So, as I mentioned in the first slides I showed, we have a semi-automatic workflow for adding software. So here in this one, we'll take a closer look. So the first step that you do is, as a contributor, is you create a PR to our EESSI software layer. Once your PR is checked out by a reviewer, they will start building it if they think it looks okay. Then the build bot will automatically submit it to all the different build cluster nodes that we have. Once the builds are finished, it will also run our reframe test suite. if the software that we are building is already an easy test suite, then it will also run those specific tests. Otherwise, it will just run default tests to make sure that everything is still working. Once these two, the build and the tests check out, the software gets signed tar builds get sent to our S3 bucket, which then gets picked up in a cron job to our Statum0 server. Then we have it opens a PR to our staging repository where people, reviewers of EESSI will do a last check that everything looks okay in the tarbles, and if this is the case, it will then be deployed into EESSI repo. Let's have a closer look at how to contribute to EESSI step by step. So before you create a PR to our software layer, you have to find or create an EESSI config file to install the software. Before you open the PR, we encourage you to test the build with EESSI extend, so that you are sure that the build with that EESSI config will work for the EESSI environment. In some cases, some things have to be changed to the software installation procedure or the software itself to make sure that it will work in the EESSI environment. If you're sure of that, then you can contribute the EESSI config to EESSI build if it wasn't in there yet. And then you can open a PR, so you don't have to wait until your EESSI build PR is merged before you can open an a PR in the EESSI software layer repository. And then you can start, if you have the rights to build, you can start the build yourself. Otherwise, one of our builders and people with the right rights can start submitting the builds to all the CPU targets. When all that checks out, the build succeeds on all the CPU targets, the EESSI build PR is merged, then we can also deploy the software in EESSI. So yeah, some recommendations which we have for contributing software to EESSI. So as I already mentioned, test locally first, so you at least know it works on some CPU targets, but this is not strict. If you can test it on multiple CPU targets, that's very nice. If you have only access to one CPU target, that's already good. Always use the latest ED build release when you're testing your EESSI config, because some things might have changed in EESSI build that might have broken the install procedure, or so you should also always rely on the latest release. As I mentioned, the pull request can already be opened in EESSI, even though the PR in the EESSI build repository is not merged yet, but deployment will have to wait until the EESSI build PR is merged. We do this to make sure that all the changes are picked up, and the EESSI config that gets merged in EESSI build is also the one that gets used for all the building of the CPU targets. If you see that there are problems on specific targets where you don't have access to, you can you can rely on the builders in our team to resolve any problems. But we also encourage people to help us find solutions. You can do this via commenting in the pull requests if you think you know what's wrong and how to fix it, or you can do this via our EESSI Slack. Yes. A detailed guidelines for contributing to EESSI you can also find in our documentation, where we have an overview of all the steps. We have also documentation on contributing to EESSI build. We have documentation on contributing easy configs. We also have documentation on using the update PR and new PR options in easy build so that you don't to create new PRs. And in 2023, we also had a tutorial on easy build where we went in detail on contributing to easy build. So if you want a more hands-on tutorial, you can also check out that. Then we also have step-by-step instructions for opening PRs to easy in our documentation that you also see. And then I will leave it now back to Kenneth, except if there are questions that we might need to answer on Slack or in the chat.
I see there are a bunch of questions coming into Slack, but as far as I can tell, they've been answered quite well by Thomas and Alan. And maybe we can cycle back to them at the very end. If there's anything particularly interesting to raise, we can go back. So let's also see this hands-on with the same easy config files that I was using during the easy extend demo. So we know that those work. At least we know that the 25A worked. So yeah, and the spec thing isn't happy here, but that's the result of a proof of concept. I think I did everything right, but we'll see what went wrong. We already saw that the scikit bio with 25A worked. It also worked with 25B. So that means we can actually open a pull request for both of them and get them into easy. So let's do that step by step. Let's first start with the 25A one, so the one that is already in easy build. What we need to do here is open a pull request to the easy software layer repository. And essentially we need to express our interest in adding this particular easy config file into easy. So the right file to do that is this easy stack file for the correct version of easy. And then also for the correct version of easy build. So in this case, the latest version 5.3.0. And the specific file for the 25A toolchain. So any easy config files that use this generation of easy config files. So what I will do here is I create a new branch. The name of the branch doesn't really matter, but to make my future self happy, I usually pick a correct name here. We stage this file, we commit this file, and there's also a sort of standard here in terms of names of titles of pull requests. So I'll try using that. So what we do is we specify the toolchain and then the name of the software we actually want to add, which, if I remember it correctly, is this one. So we do a commit. We push that branch to my fork of the software layer in the right order, of course, like this. Okay, and then we get a friendly link here that we can click to actually open the pull request. So all this pull request does is add a single line here with the name of the easy config file to the right easy stack file, and we can create a pull request for this. In this case, I'll also set the proper label. Of course, you need permissions to do this, but while I'm at it, I might as well open it. So this expresses our interest in adding this version of scikit bio to easy. And it also says it's already an easy build, so this should be working. The next step then is that somebody from the builders team will ask the bot to try testing this on the CPU targets. You can see the long list of CPU targets we have here, everything that we have in easy currently. To start off with, we pick a subset of that. So usually an x86 one. We've learned that Neoverse v1 can be tricky. And then we can actually also do NVIDIA Grace, A64 and FX, and Zen 5 in one go. So some of these are actually on different build clusters. As soon as I drop a comment like this, we should see that the bots are responding to this. I'm hoping this is working because we had to do some mitigations for the copy fail CVE that was released last week. So we had to update our clusters, of course. Yeah, but that is happening. So the build cluster in AWS is spinning up test jobs for each of these CPU targets. The one we have in Ducalion for A64FX as well. Zen 5 one as well. And there is one missing for NVIDIA Grace because it seems like the bot in Jülich is not active yet. So these jobs will now start automatically, and they will come back with either a success or a failure, and that will tell us how well we are doing. If it all comes back as a success, we can then also trigger the other build jobs and complete the effort to actually get this deployed. So of course, I won't wait for this. This will take a bit too long. Now this was very easy because this EESSI file is already in easy build. For the latest version of Scikit-Bio with the latest toolchain, I opened the pull request to easy build, this one here, which means it's not in the latest release of easy build yet, although it is being tested here, and at least the standard procedure that we have in easy build to also verify contribution seems to be happy. But this is all, of course, only testing on one of the CPU targets that we have in easy. So what we have in easy is a bit more extensive than that. So the main issue we have here, it's not in an easy build release yet. So how can we actually contribute this to easy already? It looks very similar. So let me check out our main branch here. Create a new branch. Yeah, I was actually using my aliases here. Let's do it full form, 25B. And here I already have the changes to the appropriate easy stack file prepared. So in this case, very similar, but we're of course using the 25B version of the easy stack file. And in here, you can see how we can tell easy builds to install an easy config file, but coming from a pull request. So this is the pull request that we have opened. And rather than using from PR, which I was doing manually when testing, we're using from commit here. So we're using this specific commit, which corresponds to the commit that was used in the pull request here. So this one. We use from commit to make sure that all the installations we do are done with exactly the same easy config file. So as Lara mentioned, a pull request can change over time if problems are found, patch files get added, or the easy config file gets changed to fix a problem. We want to make sure that we use the exact same easy config file for all the 15 installations that we do. So this is why from commit was introduced. So we have full control over what's being used. So very, very similar here. I can do a commit or 25B in the separate branch. I'll include everything here, push this to my fork, and then of course open a very similar pull request. So this looks very similar. The only difference is the from commit here, and of course different file because it's a different toolchain. I'll add the label here again, and then it's essentially the same dance where we ask the bot. Well, copy paste is what I used here. We ask all the bots to do the test installation of this and see if it all works out. In this case, it's actually going to be installing a whole bunch of things. I think like a dozen or so easy config files, some of which are coming from the pull request here. So you can see there's 4 easy config files included in the pull request. And other ones that are dependencies of these are not installed in easy yet. But through this single pull request here, everything will be added eventually. Now let's see, these are still waiting to be launched. Some are already running. You'll see that CI is actually failing here. So this is screaming at us. What this does, it actually verifies whether the installations are already there. So eventually, when all those builds pass, we'll trigger a deployment. And we make very sure that everything is okay by, after the deployment, re-triggering these checks here, which are running in GitHub Actions and CI, to make sure that everything is ready. So this is now telling us 4 things are still missing: Scikit-Bio itself, and then the 3 dependencies. And something similar will happen here after a while. And here you should see a dozen or so things missing in the failing tests. So you can see we have a lot of automation, a lot of checking already in place when making these contributions. Okay, so that basically wraps it up. If you need any help with this, as Lara already mentioned, you can reach out to us in the pull request if it's specific to a pull request, or in the easy Slack. But we also have our support portal, essentially, So it's actually a GitLab instance where you can either create an account and open issues, or you can just send an email to support@easy.io from any email address, and that will open a private issue automatically in the support portal. So all of this is documented on the Easy website as well. This could go about a contribution to Easy, but just general problems, general questions, or any requests for enhancements, additional software, whatever, you can open issues for. We cannot promise that we will jump on everything, and especially requests to install additional software are easy to make, but can be quite a bit of work to actually get correct if you take into account all the CPU targets that we support, for example. But it's at least interesting to know that there is a need or an interest for a particular software package. So don't hesitate to reach out to us, and we'll see how we can help you. There is actually a dedicated support team behind this, thanks to the multi-xScale Euro HPC Center of Excellence, which has also set up this support portal. Okay, and with that, I'll just want to remind you of the ongoing series that we have. So we have 3 more webinars coming up in this session. Next week, we'll look into using Easy for continuous integration and software testing. And with that, I think we can see if there's any useful or interesting questions that have been raised. So I'm looking at Thomas and maybe Alan to see if there's anything interesting. Or if anyone has questions and wants to raise them themselves in Zoom, you can definitely raise your hand as well. Keep in mind that we're still recording. And if no questions pop up, we'll close the recording and then we can go into a more informal Q&A if that's useful.
Kenneth and Lara, I think all questions that came in via Slack have been answered. But if anyone has additional questions, of course, please go ahead.
Yeah, I see that people are asking about the slides. Yes, of course, the slides will be shared on the link here. And also the recording of the session will be made available maybe today still. If not today, then definitely tomorrow. So you can watch back some demos or specific sections if you want to. If anyone has questions, yeah, raise them in the Slack channel, or if you have to in Zoom, or raise your hand if you have any burning questions or something that wasn't clear. Maybe Alan
there was a question. There was a couple of interesting questions that I raised. One was like, what's the difference in this easy config or the easy build settings between the different types of installations? And there are a couple of differences between them. I mean, the best way to look is to actually check, right? To look at to use the show config to see what the differences are. But also because it may change over time, right? Maybe we learn that we made a mistake or something is not quite the way we wanted, and we might add a new setting for a particular type of install. But there are things like, for example, the question was raised like, can I have multiple of those variables set at the same time? And the answer is depends. On what type of installation you're doing. So if you're doing a user or project install, you can have both of those variables set at the same time, but that triggers some logic. So it assumes that if you have an easy project install set, you want to use some dependencies from a project, but you actually want to install for yourself, right? And so that's if you have user install set that has a meaning inside the module. And then the other question was about tool chains that are in Easy Build but are not shipped inside Easy. So Intel in particular, and what happens with those? We don't ship it right now, and it's not impossible that we ship it. I think the licensing would allow us to ship the runtime, and so it would be possible. But right now, that's not the case. There are some people experimenting with this and have gone quite far in that experimentation, and there is an open PR for the relevant easy blocks. So you need to do some configuration of the compilers to make that work, to make it understand that there's a compat layer that it needs to use. And also there's some other things as well as regarding RPath. But that's part of the compiler configuration. So there's a PR open that tries to address that. It's not ready for showtime yet, but it's on its way.
I see another question on testing on ARMs. Yeah, like I mentioned, or like Lara mentioned, it's good to test things first locally with Easy Extend, but on whatever system you easily have access to. So whether that's ARM, Intel, AMD, whatever. If you've already done one test and it works for you, that's already quite a big step. That doesn't, of course, guarantee that things will also work on ARM, but there we're happy to help you and at least highlight any problems that we see when building on ARM. There are various ways to get access to ARM systems where you can easily try this yourself. Ducalion and very soon Jupyter and your HPC are two big ones. But also in AWS, for example, it's very easy to get access to an ARM VM. And especially if you're a trusted contributor, we can actually give you access to one of those VMs to test things yourself if you're happy to put in some effort and try to figure out the problem yourself. Very often, that may be a very tiny patch for the software or some kind of additional configuration option, or maybe avoiding a dependency or adding a particular dependency. So it's actually surprisingly infrequent that we see problems on ARM. But yeah, let's make that a conversation depending on how much effort you're willing to spend on it or how much resources you have access to. I see another question coming in from Alexander. Why is LD library path filtered? So that's actually a very good question. So here you indeed see that in our easy build configuration, we filter out LD library path. I would say that's mainly a self-protection mechanism where we want to make sure that all the RPath linking that we do was actually done correctly. Since we're using RPath linking, LD library path should be a no-op essentially, so it shouldn't have any effect at all. And we want to make sure we're not relying on that in any way. So that's one reason. Another reason is we don't want to expose libraries that are shipped via Easy to other tools. Like, for example, if you start a Vim or Emacs editor from your operating system, we want to make sure that those don't get crippled or don't start failing when you have some modules loaded from Easy. So it's a bit of a separation mechanism as well. And I saw Alan is also answering that in Slack. Yeah. Okay, if we don't have any more questions coming in, I guess we can close the session here, or at least close the recording, and see if somebody has a more informal question. So thank you very much, everybody. Let me show the last slide again. Yeah, you can still register for those last 3 webinars if you're interested in those. And if not, we can keep the conversation going in the Easy Slack. Thank you very much, everybody, for attending, and see you next week.